Hello and welcome to a new episode of TGIR RabbitMQ. My name is Connor and I'm joined by Gerhard, who you'll know from the previous episodes. And we decided to close out the year by talking to you a bit about resiliency in RabbitMQ. As always, this is going to be an episode focused on RabbitMQ. However, we are going to be using Kubernetes and the infrastructure we've built up over the previous episodes to talk about resiliency in an interesting way.
Okay. I'm really excited about this change, I have to say. It's great to listen to someone do TGIR for a change. Yeah. I'm very happy about this, I have to say, especially since this is a topic that you have been passionate about, Connor, for some months now. And everything, in a way, comes together, right? Towards at the end of season 1 of TGIR, episode 9, everything comes together, where we look at how resilient RabbitMQ is. Is RabbitMQ resilient, yes or no? And the correct answer is maybe, right?
I completely agree. And I think that's the brilliant thing about chaos testing. It really shows you how testing should be. It's exploring an unknown space. You go into testing with a whole bunch of assumptions about how a product will behave, and you validate that by exploring the very fringes of your understanding of how your code works. And we're going to be using this great framework called Chaos Mesh, which is part of the CNCF. And this is an open source framework whereby you can create chaos events on a Kubernetes cluster. It functions much the same as any other Kubernetes operator in that it provides CRDs for chaos events. So there might be a CRD for introducing a network partition, for example. And we will be using some of these as we go on today. Well, the first step, we're going to need a RabbitMQ cluster running on Kubernetes. Now, thankfully, here's one I prepared earlier. We, as always, have a make target that provides a bunch of scripts in order to set this infrastructure for you. And so far, all we've run is make base. You can do this yourself. This will create a GKE cluster running on 118 of Kubernetes. And it will install into that cluster the Prometheus stack that you saw in episode 7, complete with the RabbitMQ Grafana dashboards and the RabbitMQ cluster operator. So the first thing we need to do is create our cluster. So we're going to be creating a RabbitMQ production cluster.
Yeah, I would describe that as it's like a good starting point for production readiness. The number of nodes, how they're spread, the number of CPUs that every single node gets, the memory to disk ratio, the type of disks, stuff like that. So put together, it's a good starting point for a production ready cluster.
So our pods are finished creating now, and we should be able to see if we go to the Grafana dashboard that I've port forwarded to. If we go to the dashboards and manage, we find the RabbitMQ overview dashboard. We should be able to see that we have 3 nodes up, and without any clients, we have no incoming messages or outgoing messages. The next thing we need to do is to simulate our workload as if we were running in production. So for these kind of data safe operations, we tend to recommend quorum queues for the message storage in RabbitMQ. And we're going to be creating a client that is simulating a quorum queue load. So if I run make quorum clients, that will again just apply a Kubernetes manifest, which is just perf test, the RabbitMQ perf test, that will simulate a quorum queue workload. Okay, so now we have all of our producers and consumers up. We have our constant throughput. The next thing to do would be to simulate some kind of chaos event. The first thing to do would be to install Chaos Mesh into the cluster. And that's pretty simple to do. We have a make target for this. So if you run make chaos operator, that will install the Kubernetes operator provided by Chaos Mesh, which will create the CRDs that represent experiments. And an experiment is a either timed or instantaneous chaotic event that happens in your system. If you want to have a look at what this script does, it's provided by Chaos Mesh, and I'll show you very quickly. It basically just looks at your kube config, works out whether you're running in kind or a regular cluster provided by some kind of IaaS, and it will install the CRD for you. You can check that out there. So I'm going to go ahead and run that now. And we'll see it'll install a load of CRDs into our cluster, as well as namespaces for the chaos events, and all the resources you need to be able to create chaos.
That's a lot of stuff that gets set up in maybe a minute. Not bad for such a complicated system. Imagine what the alternative would be if we weren't using Kubernetes.
So the simplest kind of chaotic event we can create would be probably a latency event. And this would target various pods in your system and cause any traffic to and from them to be latent. We can configure how long that latency is and when we want it to come into play. Very quickly to talk about the environment that we have, I have K9s here just to be able to look at my Kubernetes resources more easily. If we look at the RabbitMQ cluster object that we just created, we can see that we have this section here, the topology spread constraints. And this just tells the Kubernetes scheduler where to schedule the pods. In this case, it's trying to evenly distribute the pods that we create with the RabbitMQ cluster across availability zones in the IaaS. So in our 3-node cluster, we will have the 3 nodes be distributed across 3 availability zones. If I run make chaos az latency, this will simulate one of those availability zones, experiencing latency to the other availability zones in the cluster. So if I go ahead and run this, we can see that we have this new object created. And if we go to our dashboard in Grafana, we will be able to see that once the latency kicks in, the message throughput will likely decrease.
One thing that I really liked about Chaos Mesh is that it has a dashboard as well. So it has a UI, and we can use that UI to see what experiments are running and what experiments are configured. Can we take a look at that now to see how does our experiment look from a Chaos Mesh UI perspective?
Yes, we can. So if I go back to our terminal, I'm going to use K9s to create some port forwarding. You can do this through kubectl yourself if you'd like. So if I go to services and I look for all of my services, there is a Chaos dashboard service that's been created in the Chaos testing namespace. If I go ahead and port forward that, that's now forwarding to port 2333. And if I now go to my browser again, go to localhost 2333, this is the Chaos Mesh dashboard that you get as part of the operator stack that gets created with that script. And so we can see the spinning circle means it's currently in effect. It is being applied to our system. And if we look at our events tab, we can see that the cluster latency experiment is still running. And it will continue to run until we delete the object in Kubernetes, or we pause it through the UI, which will do effectively the same thing.
Now that we've seen this experiment from a Chaos Mesh UI perspective, what does it mean for RabbitMQ?
I think the first place to look to check that would be the overview dashboard. And you can see very quickly that the throughput rate has dropped to the floor. Where before we had a throughput of 1,000 messages per second in and out, it has really tailed off to close to 0.
So we are pushing about 30 messages through the system. So 1 second of latency in one availability zone, this is constant latency. So it's not variable, constant. So all the traffic that enters and exits that node, can we see which node it is?
Yep, so the dashboard of Chaos Mesh will show us this. So we can look at the detail of the event, and we can see that there are source pods and target pods. So it has chosen all traffic to and from pod 2 to the rest of the pods in the cluster.
Right. So that means that all the traffic all the traffic coming from RabbitMQ node 0 and 1 into RabbitMQ 2, and all the traffic going from RabbitMQ 2 to 0 and 1 is delayed by 1 second. And that's all the operations, including the raft ones. So consensus is much slower. It's delayed by a second. Every single consensus operation is delayed by 1 second. And that's why everything slows down, not just the queues running on that node.
We can look at the CPU and memory consumption of one of the pods on the cluster to determine that it probably is running rather slowly, just because it has so little work. We have a make target for this. It is make RabbitMQ observer. And this will open RabbitMQ diagnostics observer on a random node in the cluster. So if I just go ahead and run that, if I press RR to focus purely on the reductions.
Yeah, we're sorting all the Erlang processes now by reductions. We can see that the debts opened file loop, that's the current function. The name or initial call that's in it, we don't have a name for it, so it doesn't have a registered name. It's just the initial call. That actually has the most reductions, but those are very few. So 400,000 every 5 seconds. That's like 80,000 reductions per second, which is very, very low. A process which is under significant load, we can expect to see a few million reductions per second. And we can also see the two schedulers. So this node, this Erlang VM, RabbitMQ node, we can see at SMP, it's the second row. SMP, so it's using the multi-processor architecture. There are 4 CPUs in the system, and Erlang is allowed to use 2. So we're using 2 CPUs. So we can see the schedulers 1 and 2 on the left-hand side, the ones in green. We have 2% usage and 1% usage. So very little of that scheduler time is being used.
We've had our latency applied to our availability zone, but at some point, we think that the zone will recover. The latency will drop and we'll go back to being in a healthy state. You can either do this by deleting the custom resource that represents this, or you can do this through the Chaos Mesh dashboard. I'll show you it through the dashboard now. So if I go to our experiments, and I can just pause the experiment, and this will terminate the latency on this cluster.
What other experiments can we simulate?
One of the more common failures that you can have with distributed systems are network partitions. And these are just like latency experiments, easy to create with Chaos Mesh. So if we go back to our terminal and we run make chaos az partition, what this will do is this will pretend as if a availability zone has been partitioned off from the other 2 availability zones. So if I run that again, it has created our object which represents the chaos event. And if we go to our Chaos Mesh dashboard, we should be able to see, if we refresh, our new experiment appearing in the UI.
There is a better dashboard that we have for this specific thing, which is the Erlang distribution. And if we look at the last 5 minutes, we can see here that we have 6 distribution links. So that means 3 nodes, and only 2 are established. So 0 to 2 and 2 to 0, that's the only one that's established. So RabbitMQ1 is the one that was partitioned from the other 2 nodes. Right, so we can see now that the nodes are exchanging very little data. We can see data sent to peer node that went from about 500 kilobytes per second, before the partition, to 13 kilobytes per second. So I'm assuming that the clients, what are the clients doing now? A perf test.
So we can see that the throughput of the cluster has actually dropped to 0, and the number of ready messages has risen to about 5,000, and appears to be sitting pretty consistently at that point.
We're still seeing 3 nodes there, and that's right, because the nodes themselves, like the node itself, it's still sending data, it's still sending metrics, because it's running. It just can't talk to the other nodes. So from this perspective, we're seeing 3 nodes because the node is up. It's emitting metrics, it's running. What we're not seeing is in this dashboard how it's been partitioned from the other 2 nodes. And that's where Erlang distribution comes in, which shows us what's happening from an Erlang distribution perspective. The messages which were in flight were not confirmed by consumers. So that means that they are back with the queues, in the queues, ready to be delivered to consumers. We can see the distribution as well. So most of them are on the blue one, which is RabbitMQ2, almost half. And the other half is on RabbitMQ0. But there's no messages, no ready messages on RabbitMQ1. And that will correspond to the queues, the queue leaders if we go down to the queues graph, total queues. Now this is a little bit misleading because apparently we have more than 100 queues. What that means is that there are queue leaders on RabbitMQ1 which are in this unknown state. So they're still there, but they won't be servicing any requests because they can't reach any of the other nodes. Meanwhile, we can see that the green node, which is RabbitMQ0, it added 33 more queues. So now it's running 66 queues. And what it means is that all the queue leaders which are running on RabbitMQ1, and they're still running there, they're no longer acting as queue leaders, but they don't know that because they couldn't communicate with the other nodes. So they couldn't determine that, hey, I'm no longer a leader. Why don't we have any messages being published or consumed?
This may well be an artifact of the client we're using to connect to this cluster. If we look at our terminal again, we go back to K9s just for an easy way to check on pods. We can see that the perf test pod has had 5 restarts.
If we look at the logs, what do we see when it restarts? The broker is giving a 541 error code. And what that means is that it can't service the request. And the reason why it can't service the request is because some connections were made to RabbitMQ1, the partition node, and that partition node cannot service any requests because it's in a minority. The node is still available, it's still running, but perf test, when it sees that, it crashes. It's an exception which it cannot catch. The right thing to do would be to try and rescue this exception and try and reconnect. So I know that some threads are connecting. So some connections are successful and they could make progress because the ones made to RabbitMQ0 and RabbitMQ2, they could make progress, but because some are established to RabbitMQ1 and we're not handling this exception, it just crashes. I think this is also linked to the network partition handling strategy we're defaulting to ignore. We use ignore so that we don't throw away any data. It is possible that while a partition is happening, some messages arrive on that node or some queue declarations are made on the node which would stop itself and then restart itself and then resync. And we could be throwing away some data. So rather than doing that, we're leaving everything as is, we're surfacing the problem and we're letting someone decide what to do about this event. So we could fix the partition and see how our system behaves afterwards.
This time, instead of deleting the partition through the chaos mesh dashboard, I'm going to do it just through a make target. If you run make clear chaos, it will just delete all of the chaos experiments that are on your system right now. So if I do that, it will go ahead and delete all the ones that we have defined so far. We should be able to see in the logs for the pod that was partitioned a amnesia inconsistent database log.
That's a good idea. Let's have a look at that to see what we see in those logs.
So 1 was the node that was partitioned.
Mm-hmm.
And if I scroll up, there you go, amnesia inconsistent database. So this is the node reconnecting. I believe it's every 60 seconds it tries to reconnect to nodes that it was previously connected to. And once it finds these nodes, it does a database sync to see if it is indeed in sync with those nodes or whether a partition has occurred. And it sees that the database is inconsistent, determines that it is the minority partition, and as such does not sync with the rest of the cluster. It just maintains itself as separate from the rest of the cluster.
Yeah, that's right. Until someone intervenes and restarts the app, for example. How can we restore this node? How can we manually restore this node? Well, what I would do is open a shell. That's the easiest thing. RabbitMQCTL stop app. And RabbitMQCTL start app. And if we look at the logs now, what do we see?
So we can see this new node detecting new leaders in the other nodes in the cluster that it's now reconnected to. And it looks like connections are now being created, as presumably the perf test app has come back from its crash loop and is now consuming and publishing as it was before. But crucially, no data has been lost. Only availability has suffered here. And we will quickly return to the 1,000 messages per second that we were at before.
We can rerun this with pause minority. Pause minority gives you a false sense of security in that it will do the right thing. But there are scenarios where when it won't do the right thing, or it won't do anything at all, and it gives you that false sense of security. So ignore, while it is inconvenient, it just shows you what happened and it won't do anything. It will let you decide what to do about it. In the absence of something better, I think that one has the least disadvantages. If inconvenience is not a big disadvantage to you. So that would be my summary. And auto heal will only heal at the end of the partition, and anything that happened in that duration from the partition starting, the partition ending, all that will be lost, all those operations. And that's possibly the worst one, if you care about consistency. So now we have pause minority. So what happens? I mean, you can start again. Like, let's apply this chaos experiment and see what happens. What does it look like from the Erlang distribution perspective? That's an interesting one when we're talking about what happens in the cluster. Right, so what we're seeing here is that 1 is no longer emitting metrics. So in the state of distribution links, where you see those squares, the first 2 rows, there's nothing there, which means that we're not getting any distribution links metrics from that node. RabbitMQ1 is down. And we can also see that RabbitMQ0 to RabbitMQ1, it's connecting, it's trying to connect, but because the node is not there, it can't. And the same thing for RabbitMQ2. So this determines RabbitMQ1 being stopped. And we can see data sent to peer nodes. This is perf test that reconnected, I'm sure. May have crashed, I don't know. But there's traffic flowing through the remaining 2 nodes. And if we look at the RabbitMQ overview, we'll see messages per second. So we have 2 nodes, but the publishers, the consumers are running. Yeah, everything restored, everything back as it should. So this is good. We do like this. And when the 3rd node will come back, nothing will change from the perspective of the clients, because they're all connected, they're all running. Now all the load will be running through those 2 nodes, especially the connection related load, but the 3rd node will contribute to the quorum queues.
Now this node coming back hasn't actually triggered any rolling update of the stateful set of the cluster. So what that means is the queues will probably be unbalanced between the nodes that are currently up. If we scroll down to total queues, you can see that when the partition occurred and the minority node was paused, all of the queues were transitioned to the node 2 here. And so if we wanted to be completely safe and back in a position where we were happy with the equal distribution of queues, we should run the rebalance queues command again. So we can very quickly do that. And we're back at an even distribution of queues. One of the great things about Chaos Mesh is that the selection of pods that are sources for the Chaos experiment and targets for the Chaos experiment are arbitrary. You can use any Kubernetes native selector, such as labels or namespaces and names of pods, to select your sources and targets. And that means we can create network partitions in very interesting ways. Instead of creating essentially 2 subnets, one with 2 nodes and the other with 1 node, we can just create a partition between 2 nodes in the cluster and leave the rest of the connections within the cluster intact. Now you might be thinking, well, why would this ever happen? Surely if things are affected on a availability zone scope, then surely it would affect the entire availability zone and all the connections to and from it. And that's not actually true. Cloudflare is the most recent example of this, where they had a misbehaving network switch that was causing packets to be dropped only between two nodes in a distributed cluster. And we're going to recreate that with a chaos experiment. So if I go to our terminal again, I run make chaos intranode partition. This is going to select two nodes in the cluster and create a network partition between them, leaving all the rest of the connections intact. And this is going to lead to where all the nodes in the cluster, all the healthy nodes in the cluster, cannot agree on the state of the cluster.
In very simple terms, let's take RabbitMQ 0 that sees RabbitMQ1 to be healthy, but RabbitMQ2 sees the same RabbitMQ1 to be unhealthy. So the three nodes, they can't agree whether RabbitMQ1 is or isn't healthy. And that's what we're simulating. So RabbitMQ1, I'm assuming this is a good time to check to see which two nodes are partitioned amongst themselves. So if you go to the Chaos Mesh dashboard, what event do we have right now? So in our case, RabbitMQ1 is partitioned from RabbitMQ2. So as I was saying, RabbitMQ0 sees RabbitMQ1 to be healthy and it can communicate with it, but RabbitMQ2 cannot talk to RabbitMQ1. So RabbitMQ2 thinks that RabbitMQ1 is not healthy.
We should be able to see this break in communication in the Erlang distribution as well, as we did before with the other partitions. Our strategy of pause minority is going to slightly encumber us here, because there is no true minority within this cluster. There are three nodes, but none of them are completely partitioned off from a majority of nodes. However, it looks like node 1 has decided that it is in this state and has paused itself thinking that it is partitioned off from the rest of the cluster, when in fact it is only partitioned off from node 2. And so you can see that it's not reporting any metrics because RabbitMQ stop app has been called on that node.
I was not expecting that, to be honest. I was expecting it to not know what to do. And we can see that in this graph, RabbitMQ2 to RabbitMQ0 is still communicating. No, that's not the one. RabbitMQ0 to RabbitMQ1 can communicate.
And I think this is a great example of something where chaos testing can kind of highlight expectations or assumptions made in the way a system is architected. I think Rabbit in its current state right now is assuming that partitions can only ever happen in the way that we mentioned before, where you have two subnets of nodes. Instead, we have just a single link down, which, as we've seen, can happen in real life. And it behaves as if we were in the former situation.
So what does RabbitMQ overview do? I'm very interested to see what can we see in RabbitMQ overview?
So,
okay, this behaves well. This behaves well. So pause minority is behaving correctly in this scenario. Very interesting.
It certainly seems like for this application of this client and the way it is set up, it does seem like if you're favoring availability, certainly, then pause minority is the way to go for this cluster, especially since, well, the readiness probe will fail once the app is stopped and paused because of pause minority. And so the service will no longer redirect traffic to it. So if you are favoring availability, then pause minority definitely is the better of the two. And certainly this app confirms that. But if you desperately can't lose any data, then you still will suffer if you are not using ignore.
So if we were to stop this experiment, do we see our cluster restore itself? And I think the answer is yes, but let's be certain that that's what happens.
Okay, I'll run make clear chaos just to remove all of the chaos events that we've had. And perhaps the best place to look will be this view in K9s, where we see the readiness probe for the pod 1. And we should see that once the nodes are reconnected, then we see the readiness probe passes because the app has been restarted due to the cluster partitioning handling strategy.
Mm-hmm.
And looking at the dashboard, we were already running on a quorum of nodes, so there shouldn't be all too much that happens here. We will notice one node will come back up as reported here. And there you have it. But the throughput will be unchanged. The consumers and queues will be unchanged, but we probably will still have the issue we had before where the the queue leaders are not balanced equally.
While we tried only 3 experiments today, there are others that we've included, which we just don't have time to cover. So if we look at what other targets we have available, we can introduce, I believe, CPU stealing. We can introduce slow disks, add latency to our file I/O operations, memory filling. So we have a couple of other experiments that we could run. And while we say we're referring to the royal we, including you, right? We, the RabbitMQ users, we, the RabbitMQ community. So it'd be very interesting to know if you do run some of those experiments, what do you get? How does RabbitMQ behave in that case on your hardware, with your setup, maybe even with your clients or with your type of workload that you can simulate using perf test or even using your own clients? Why not?
With that then, I'd like to say thank you very much for joining me. I hope you've learned a lot about chaos testing and how you can perform your own testing with Chaos Mesh and RabbitMQ on Kubernetes. And thank you, Gerhard, for joining me.
Thank you, Connor, for hosting a great TGIR episode. I believe this is the last one for this year, and that should wrap season 1. And I'm looking forward to the next episodes that we'll do together.
Thanks once again for watching, and we'll see you next year.